Bismillahirrahmanirrahim. Assalamu alaikum, students. In the last lecture, we started with the idea of polarization. Today, I continue with that. I write continued. In the last lecture, under this heading, we defined atomic polarizability alpha. We solved a problem related to that. Today, under this heading, we will first discuss the alignment of polar molecules. Alignment of polar molecules. We have already discussed that when a neutral atom, which has no dipole moment to start with, is placed in an electric field and induced dipole moment is created in the atom by the applied field, there are some molecules which have built-in permanent dipole moments. For example, in case of water molecule, for example, the electrons tend to cluster around the oxygen atom. Let me show a figure of oxygen molecule. So it has oxygen atom. This is O, and it has two hydrogen atoms in it. As you know, let this be one of them and this second one. This is O negative, and these are two H positives. This angle is 105 degrees. And it has a dipole moment in this direction. So let me name it figure 1. So in the water molecule, electrons tend to cluster around the oxygen atom as shown in the figure. And since the molecule is bent at 105 degree, this leaves a negative charge at the vertex and a net positive charge on the opposite sides, right? The question is, what happens when such molecules, which we call polar molecules, are placed in an electric field. We've already discussed it, you know it from your previous classes. Still, I am talking about it so that I can move forward. So if the field is uniform, the force on the positive charge, the force on the positive end F plus, which is QE, exactly cancels the force on the negative end. Right? It is F minus equal to minus QE. Let me show it in the figure. We name it figure 2 and draw a electric figure here. So this is minus Q. This is plus Q. And this is the vector T. And this point 2 is the center. So when you place this dipole, for example, this water molecule, any polar molecule in a uniform electric field E, plus Q will experience force in the direction of the field. We denote that by plus, and minus end or minus Q charge will experience the force in the opposite direction of equal magnitude. The field is uniform. So these two forces exactly cancel out. So this is our figure 2. Plus Q experiences plus F, minus Q experiences minus F. This is the direction of the field. We're assuming field is uniform. This is the separation vector D. O is the center. However, there will be a torque given by, I will write it directly. However, there will be a torque tau given by tau is equal to E cross E. Let me circle it and name this equation 1. What is P? P is QD, the dipole moment of the molecule, and E is the uniform electric field. Remember, this is the torque experienced by the polar molecule about the center of the dipole. Write it here, about the center of the dipole, right? Note that tau, the torque, is in such a direction as to line P parallel to E, right? Because when P is aligned in the direction of E, torque will become zero. So a polar molecule that is free to rotate will swing around until it points in the direction of the applied field. You need to remember it. A polar molecule that is free to rotate will swing around until it points in the direction of the applied field. Right? Now, if the field is non-uniform, so that F plus does not exactly balance F minus, there will be a net force on the dipole in addition to the torque, right? So we write it, if the field is non-uniform, so that F plus does not, this is here F plus, does not exactly balance F minus, there will be a net force on the dipole in addition to the torque. In addition to the torque, right? And of course, E must change rather abruptly for there to be significant variation in the space of one molecule. So this is not ordinarily a major consideration in discussing the behavior of dielectrics, right? And for a perfect dipole of infinitesimal length, this equation 1 gives the torque about the center of the dipole even in a non-uniform field, right? So in non-uniform field, there is a net force in addition to the torque, but this expression for torque gives the torque in case of uniform as well as non-uniform field, provided dipole is of infinitesimal length, right? Let us move to now the definition of polarization, which was our main heading. Let me use another color. So how we define now polarization? Now as we have considered the effect of an external electric field on an individual atom or molecule, we are now in a position to answer qualitatively the question, what happens to a piece of dielectric material when it is placed in an electric field? We write it, what happens to a piece of dielectric material when it is placed in an electric field. This is our question. If the substance consists of neutral atoms or non-polar molecules, the field will induce in each a tiny dipole moment pointing in the same direction as the field. Of course, if the molecule is asymmetric, the induced dipole moment may not be parallel to the field. We have already discussed that with the material, if the material is made up of polar molecules, each permanent dipole will experience a torque given by the expression tau is equal to P cross E, tending to line it up along the field direction. Now, as you know, random thermal motions compete with this process, so the alignment is never complete, especially at higher temperatures, and disappears almost at once when the field is removed. So notice that these two mechanisms produce the same basic result. What is that basic result? A lot of little dipoles pointing along the direction of the field, right? One mechanism is of induction, second is of the orientation by the torque. So what we get out of these two mechanisms, a lot of little dipoles pointing along the direction of the field. So when we get this situation, we say the material is polarized. So the material becomes polarized. Now we define a quantity which gives a convenient measure of this effect. What is that quantity? That quantity is dipole moment per unit volume. We denote it by capital P. The vector quantity. It is called polarization, right? So what is polarization? A vector quantity denoted by capital P, which by definition is dipole moment per unit volume produced in a material which is polarized because of the two mechanisms already discussed, right? Next we have the field of a polarized object. By field we mean electric field. So question is like this. Suppose we have a piece of polarized material. Suppose we have a piece of polarized material. I've already discussed by that what we mean. That is an object containing a lot of microscopic dipoles lined up. The dipole moment per unit volume is called polarization. The dipole moment per unit volume, capital P, is called polarization, is given, right? So we have a polarized material, dipole moment per unit volume, capital P, which is also called polarization, is given. The question is, what is the field produced by this object? Not the field that may have caused the polarization, but the field polarization itself causes, right? We want to figure out that. What is the field produced by this object? We know that what is the field of an individual dipole. So one way to get the field of this polarized material is to break the material into infinitesimal dipoles and integrate to get the total field. As you know, it's always easier to work with the potential. So for a single dipole, how we write the expression for the potential? For a single dipole with dipole moment little p, I should write it, it is here dipole moment. Now here are two p's moving in the equations. One is dipole moment, second is polarization. Capital P is polarization, small p is dipole moment. So for a single dipole with dipole moment p, the expression for potential is given as this is the expression. Let me name this equation as equation 2. Then circle it. Remember, this P is here, dipole moment of the dipole under consideration. And one more thing, I have written two kinds of R's. This R inside this bracket locates the point at which we are finding the potential. This R is the distance from the dipole to the point in question. And this R cap is a unit vector in the direction of this R, right? Let me show a figure. We have used figure 1, figure 2, so that will be figure 3. So we have some polarized object. This is my figure 3. We want to find its field. We are talking in terms of potential. You know, we can switch from potential to field and field to potential. Electric potential is a scalar corresponding to the vector field. So we are talking in terms of electric potential. So we have a polarized object. Its polarization, that is dipole moment per unit volume, is given, and we are interested in finding its field due to that, or potential due to it. So we said we can do one thing. We can divide this polarized object into a large number of tiny dipoles and first find potential due to one dipole, then integrate over the whole polarized object. So we are showing one dipole having dipole moment P, little p, distinguish between little p and capital P. This is dipole moment here. And we have some point. R distance from the dipole, this R. So we are interested, initial vector R. We're interested in finding the potential due to this whole polarized object. Let me write it. This is a polarized object. Because for single dipole, this is the potential expression. Now, in the present context, we have a dipole moment. We have, or I should write, for the polarized object, we have a dipole moment, little p equal to capital P times d tau prime in each volume element dt prime. Understand it? We are dividing the object into infinite small volume elements. Each element is dt prime, d tau prime. This is tau symbol. So if its polarization per unit volume is capital P, if you multiply that polarization by the volume element under consideration, you will get the dipole moment of that particular volume element, right? So the total potential, how you can get it at the given point in question, it is simple. V of R is equal to 1/4 pi epsilon naught. Here you write capital P, this capital P polarization of R prime times, first we dot it with the unit vector over R square times d tau prime, then we integrate it over the volume V, or let me represent this volume by this appears to be new. I will write it italic V, right? Where this italic V is the volume of the object, polarized object. Let me encircle it and explain it to you. So it is simple. We wanted, let me name this equation 3. We have a polarized object with given polarization. We want electric potential due to this polarized object. We divided it into infinitesimal volume elements d tau. Now the dipole moment small p per volume element is capital P times d tau, and equation 2 gives the expression for potential due to a single dipole with dipole moment little p. So if we have to find the potential at point R due to whole object, what we did, we found first the potential at the given point due to single volume element d tau prime, that is without this integral 1 by 4 pi epsilon naught capital P, which is polarization dotted with the unit vector over R square. Then we integrate over the whole volume italic P. This gives us the potential at this particular point due to whole polarized object. I want to first emphasize this R locates the point at which we want to find the potential. This R is the distance from the dipole to the point in question, and this is the unit vector. Primary coordinates locate the volume element. This here P R prime. R prime locates the volume element d tau prime. So capital P R prime is the polarization at the location of the volume element d tau prime, right? Let me check this expression. This is okay. But keep the track of these P's. This capital P is polarization. Small p is the dipole moment. So this way we can find the potential due to the whole polarized object. But it turns out, I will write it directly, it turns out that we can write the potential due to the polarized object as, this is okay, it's not wrong, it's okay, but it turns out that we can simplify our job. We can write this potential as VR is equal to 1 over 4 pi epsilon naught closed integral sigma b over R dA prime plus one over 4 pi epsilon naught volume italic V rho B over R d tau prime. Let me write it clearly. D tau prime. And then circle it first, then I will tell you what is the meaning of it. Let me name it equation 4, where sigma B is capital P, which is polarization of the object, dotted with n cap, and rho B is minus times the divergence of the polarization. N cap is the normal unit vector. Let me explain it. If you see this first term, this is surface integral. What is sigma B? This sigma B is actually surface. Sigma stands for surface charge density, right? dA is the surface element. R is, so we have a surface. This is surface integral. So this first term is the potential produced by the surface charge density sigma B, where sigma B is P dot n cap, P being the polarization, n cap the unit normal vector, right? And this term is a volume integral. It is a potential produced by the volume charge density rho B, where rho B is equal to minus divergence of the polarization, this thing, right? Primary coordinates locate the charge distribution. You know that. Let me check it. 1 by 4 by epsilon naught surface integral. Surface is closed. That is why there's a circle on the integral, right? This okay. So conclusion is that the potential and hence also the field of a polarized object is the same as that produced by a volume charge density rho B equal to minus times divergence of polarization plus a surface charge density sigma B equal to polarization dot n cap. So instead of integrating the contributions of all infinitesimal dipoles as in equation 3, this one, we could first find those bound charges. This rho B and sigma B are called bound charges, and then calculate the fields they produce in the same way we calculate the field of any other volume and surface charge. I will write it. It is important. Conclusion, we use this color. Conclusion. The potential and hence also the field of a polarized object is the same as that produced by a volume charge density rho b equal to minus divergence of the polarization of the object plus a surface charge density sigma b equal to p dot n. P is the polarization and cap is the unit normal vector to the surface. So instead of integrating the contributions of all the infinitesimal dipoles, as we already discussed, using equation 3, we can first find these bound charges, rho p and sigma b, rho p and sigma b, they are called bound charges. Then we can calculate the fields they produce. In the same way, we calculate the field of any other volume or surface charge using equation 4. This equation 4, this conclusion follows from this equation 4. We have not proved it, we have directly wrote this equation, right? So you remember this. You can check from any book, there is a proof for it, but we are not discussing the proof. So I summarize today's lecture. So first we said if there are polar molecules like water and they are placed in a uniform electric field, what happens? There exist two forces on plus end and minus end. They are equal and opposite. Net force on the dipole is 0, but there is a torque which exists about the center of the dipole. The torque is given by tau P cross E, which has tendency to align P in the direction of E. P is the dipole moment of the polar molecule. So if it is free to rotate, it will swing until it points in the direction of the applied field. If the field is non-uniform, then these two forces F plus and F minus will not cancel out. So there will be a net force in addition to the torque. Torque still be given by P cross E for non-uniform field as well, provided the dipole is of infinitesimal length, that is perfect dipole. Then we said due to these two mechanisms, one is the creation of induced dipole moment, and second is the alignment of the already existing polar molecules in the direction of the field. So what happens to the piece of a dielectric material due to these two mechanisms when it is placed in an electric field? What happens? We get a lot of little dipoles pointing along the direction of the field. we say material becomes polarized. So its convenient measure is given by the quantity called polarization, which is by definition the dipole moment per unit volume. We then discussed the field of a polarized object. So there our question was, suppose we have a piece of polarized material, the dipole moment per unit volume P is given, how to get its field or potential. So one way was to divide this object into infinitesimal dipoles. First find the dipole, this potential due to single volume element, then integrate over the whole volume of the object as indicated in equation 3. Then we said it turns out instead of doing this we have another way. Another way is we split the potential into two parts, one due to the volume charge density rho b and second due to the surface charge density sigma b, which are called bound charges, where rho b is given by minus divergence of p and sigma b is given by p dot n cap. So this is all for today. Prepare your exams, go through all the video lectures, don't waste your time, and don't forget to subscribe and like my channel. You can also comment in the comment box. Thank you. God bless you. Assalamu alaikum.